to, I can speak without this, if it is possible, I don't know. I can't speak loudly, so sometimes it is better because I should talk. And today I will speak. It is written in mathematical sense, spectral analysis of the 2 and 3 particle Schrödinger operators. No, but it's possible to call it is two threshold effects in the spectrum of 2 and 3 particle Schrödinger operators or 2 and 3 particle systems. No, but I would like first of them to thank Chief of Department to you and to Chief of Department of the University UTM and Dr. Professor Zainal for invitation and for the possibility to have a lecture in the Ibn Sina Institute. I taught in the faculty that Ibn Sina was born in Bukhara. It was very interesting. Bukhara belonged to Uzbekistan, and Bukhara not far from Samarkand, only about 300 kilometers. And so we know many, one of the good and big cities of the Uzbekistan, Bukhara. Yes. And Ibn Sina studied, it's written here, studied Bukhara and sometimes lived the time in Iran also. And it was very strange when Professor told me that Bukhara is still in Uzbekistan. It was very strange because of yes, sometimes it was war. Anytime Bukhara sometimes belonged to other country, maybe Arabic was here in Bukhara. People, because of religion, come from Saudi, from Arab countries, and many people, Arab people, here in Uzbekistan. And after then come Genghis Khan, you know, maybe about Genghis Khan, Mongol people come to Samarkand, and it was more than 100, about 200 years, Genghis Khan and his grandson was in Uzbekistan. At that time it was called Khorasan, sometimes Nahor, and after that appeared and Timur, you know that, and he was also not only in Iran, in Iraq also, and he has have big military also, and he did big state. But it is more interesting, his grandson Ulbek, which I have seen here, was Samarkand, and he was scientist. It is more interesting. Okay, now I will speak about some mathematical results in the because of these problems. First of them, I would like first of them, goal. Goal is this. Can you see?
Focus.
My goal is here. It is written. The main goal of this report to give some threshold phenomena. Those are not present for the 2 and 3 particle discrete Schrödinger operators associated to the Hamiltonians of systems of 2 and 3 identical particles. on d-dimensional lattice that D interacting via pair short-range potentials. And but first of them, some motivation. It is very important because of
bigger. More.
Okay, I will here. And so, there is very interesting paper. It was published, you know, that in the Letters Nature, volume 441, in June 2006. This paper is called The Repulsively Bound Atom Pairs in Optical Lux. And they exactly wrote in the abstract, throughout physics, stable composite objects are usually formed by way of attractive forces, which allow the constituents to lower their energy by binding together. Repulsive forces separate particles in free space. However, in structured environment, such as a periodic potential and in the absence of dissipation, stable composite objects can exist even for repulsive interactions. It is some of the motivations, and after then appear many papers in good journals, and one of the, and also there is 20 international conference, on atom physics, and also 2006 year, Innsbruck, Austria, and here date. And they also reported about these results in the Congress, and here it is written also. First of them, what is new? Something should be new. And he explained that they observed a novel kind of stable bound states. And two atoms in optical lux can be combined to form a pair of by repelling each other. This pair is stable and behaves and looks almost like a normal diatomic molecule, but it is not. Why? It is binding energy has a wrong sign. I will explain in mathematical sense after that what it means also. And it is also written, it is more important, what is strange about that? In free space, repulsive pair cannot exist. In free space, in the repulsive, it is not possible. But if you bring two objects together, which repel each other, they will just accelerate away from each other. In free space, two objects fly apart when they repel each other. In the spatial environment of the optical lattice, this is no longer possible because the kinetic energy of the atoms is restricted to certain ranges, known as block bands. In order for the atoms to separate in order. So they have to get rid of the potential energy from the repulsive interaction. Since this cannot be transferred to kinetic energy, and The system is essentially free from dissipation of energy by other means. The atoms have no choice but to stay together. They explain such, and I will show some pictures also what is optical lattice and other things. And for his experiments, they use a rubidium Bose-Einstein condenser. It's called sometimes BEC, which they load in an optical lattice. It is also some applications, and he told their relevance for science and technology. And they write that their findings are also relevant for current research on how to build a quantum computer, and especially in how to use atoms in optical lattices to model very complicated system from solid-state physics. For example, atoms in optical lattice can be made behave like electrons in the lattice structure of solid-state materials. And it is also explained that in the future, this system could be used as a quantum simulator to model systems such as high temperature superconductors. You know, it is very important to use superconductors and other more exotic materials. And you write also, their work opens many possibilities for the investigation of repulsor objects in this different system. Also, objects involving more than two atoms. I will say about also because of I will say about three atoms, three particles also. This phenomenon will be quite general in optical lattice physics, and also the bound states that are not stable in the equivalent solid state system should be observable in our experiments. It is more important and interesting the Bose-Hubbard model which we use to describe the repulsive pairs is also in theoretical basis for these other applications. In this sense, our work, his work, their work exemplifies the important correspondence between Bose-Hubbard model and atoms in optical lattices, and helps pave the way for many more interesting developments and applications. It is some motivation, and this research group, this research was done in a collaboration of theoretical and experimental physics group at the University of Innsbruck, Austria, and they was supported by Austrian Science Fund and by the European Union in the frame of the molecular scan work. It's okay. No, it's some motivation. But I would like, maybe sometimes it's better, I would like to show some pictures also. There is. But first of them, I would like to say no, little bit mathematics. What is Bose-Hubbard model? Bose-Hubbard model describes some physical systems with conserved number of particles. First, I would like to consider the Bose-Hubbard model, the discrete Schrödinger operators, but only two particle discrete Schrödinger operators first. And let ZD be the d-dimensional hypercubic lattice, and TD, you know that it is dual group of ZD. It is called, more time, it is d-dimensional torus. and the n-body problems on lattices can be reduced to the effective and partial Schrödinger operators. And how it's possible? It is there underlying, there is Hilbert space, L2 ZTN. This Hilbert space is decomposed as a direct von Neumann integral as stated with the representation of the discrete group ZT by shift operators, because there is shift operators in ZT, also in RD. So this Hamiltonian Hn decomposed by the Neumann integrals by Hnk decay. And in contrast to the continuous case, in this case, the corresponding fiber Hamiltonian Hnk as stated to the direct integral decomposition, they were parametrically on quasi-momentum k. Here, k in the physical literature is called some quasi-momentum. There is momentum, and there is also quasi-momentum. And in lattice case, it's called momentum, called quasi-momentum. And it is down in this paper, and first of them in my paper, it's down, and after second paper, it is alveolar LAKAEV and momentum, and the journal Annals Poincaré, 2004, and it is also done for two-particle Schrödinger operators. Particles is arbitrary, and in this paper, communication mathematics it is published in the 6th year. Now maybe it's better. Okay. Okay. Well, I thought that in physical literature the parameter k is called and particle quasi-momentum, and the corresponding this operator is called fiber operators or Schrödinger, discrete Schrödinger operators.
Maybe first of them into picture. Because of
first of them, what is optical lattice? It is very difficult to maybe, yeah, it is, should be such kind of particles in optical lattice. I will show another what is exactly optical lattice. And because of why two particles can bond, here. It is optical lattice, and here particles can be maybe here and here, only here not bound states, but here two particles repel each other, but they have bound states. It is news what has been discovered in Australian physicians. That it is bound status. It means that it is some new object, composite object, and it is new particle. It is to say new particle. It is easy, no, but it is new composite object, and every more things exist as bound state only. And so, but more time, every time they explain, people explain and investigated that all the attractive potentials can have bound state. But these Austrian physicians discovered that if particles with repulsive interaction also can have bound state. No, it is not in free space, only in optical lattice. Because of I am showing what is optical lattice in that case. Okay, and here also. So here also, it is optical lattice. This is here particles along, not bound states here, no, but here particles already have some bound states. Here bound state and here also bound state. Two particles now there is bound states. This bound states of two particles. So okay, and now two particle discrete Schrödinger operators, and there is experimental results how it is possible to justification these experimental results. They also mention that they consider Bose-Hubbard model, and they write not so much. It is physicists no. I would like to say about strong mathematical results for the two particle discrete Schrödinger operators for the two Bose-Hubbard model. Not only when two particles interact with zero range potentials, in general case also. Yeah. We consider this space, it is Hilbert space of the square integrable even functions on the torus, and here H2K, it is discrete Schrödinger operators, and this discrete Schrödinger operator has this form. Here H20K, it is Hamiltonian, when two without any interaction. Two particles, when two particles free. In this case, it is almost the same, maybe anybody to understand. It is kinetic energy operator. Yes. In continuous case, it is kinetic energy operator. In this case, it is also similar to kinetic energy operators. Plus, and it is non-perturbed operator, and here we have also perturbation operator. Perturbation operator, I write here as mu multiplied to v. Mu is coupling constant, it is some constant mu, and v is interaction operator and interaction energy of two particles. So, and this free operator, it is in our case, it is multiplication of some function epsilon k u. K is, you know, that parameter, and in the x also in Hilbert space L2 E T, there epsilon k p has this form and epsilon p has this form. This function is a very simple case here. It is simple form. Now, the operator, interaction operator. Interaction operator is, you see that it is convolution operator, convolution function. there is convolution and convolution in applied mathematics. So very important. Here we consider convolution. No, consider interaction operator should be convolution type operator because of this operator commuted with shift operators, and so this function depends on the difference of p and minus 2. So it is difference convolution operators. And I suppose that B is even continuous function on the torus to D, and mu sometimes it is positive coupling constant, sometimes it is negative coupling constant. It is very important if we consider B is positive function as positive function B. In this case, if mu is positive, the relation in this case where we consider two bosons, and if mu negative, in this case, it means that we consider two fermions. Only here dependence was here, and result in fermion's case and boson case it is difference. No, but I will consider only boson case here. If maybe I will tell you a little bit about other case, fermion case also. So this two-particle Hamiltonian two-particle operator has spectrum. Here, first of this spectrum, it is sometimes in mathematical sense it's called essential spectrum, but it is a spectrum where two particles moves free. What is spectrum? Spectrum is values of energy of particles. In classical mechanics also, spectrum, there is energy function, and values of this function, it is spectrum. But in classical physics, spectrum should be only continuous. Some should be continuous. No, but in quantum case, it is not only continuous. If particles move freely, in this case, they have some continuous spectrum. It's called scattering continuous. This segment called scattering continuous because of two particles scattering, and in this case appear on this spectrum, this energy levels. No, but in quantum mechanics, it is more important. Without continuous spectrum, operator has discrete spectrum also, discrete values. It is discrete values of the spectrum. It is energy levels of the bound states. How you should prove? You should prove if the existence of bound states. You should prove that there exists eigenvalues of the operator and eigenfunctions correspond to the eigenvalue. So it is continuous scattering, continuous spectrum. And here, if we consider positive V, in this case, from Minimax principle, here is that there is all isolated eigenvalues of the finite multiplicity, like above, if mu is positive, above the upper edge of two-particle continuous continuum. Here, okay, here should be some theorem. I would like to explain a little bit. Okay, what is difference, mathematical difference in attractive case, and if we consider Euclidean space, in this case, this operator will have continuous spectrum here from 0 to infinity. And eigenvalues maybe appear only here. Discrete spectrum can appear in continuous case. Discrete spectrum can appear only here, below the bottom of the two-particle continuum or two-particle essential spectrum. In the lattice case, continuous spectrum, it will be from here epsilon minimum k in my case, here, and epsilon maximum k. Continuous spectrum energy of free particles will be this, and discrete spectrum in this case may appear here, and also it is very important and here also. So this model can describe this also. If you consider repulsive interaction case, in this case discrete spectrum should appear here. If we can prove there is here some eigenvalue, it means that two particles which repel each other have bound states. Here it's okay. It related to this case related to the attractive potential case. If discrete spectrum is here, it is related to the repulsive potential case. So in this model, in the lattice case, it is possible. If you consider normal Schrödinger operators, it is not possible to appear here some eigenvalues because of every time here continuous spectrum. So first theorem, which is known as strong mathematical theorem, we consider case d equal 1 or 2. You understand that it is easy to understand here when the dimension in physical, I don't know how physicians, people can explain dimension 1 and 2. Here, very big difference when you consider dimension 3. And in mathematical sense also, in mathematical sense it's possible to explain, but in physical, I don't know how it's explained. So, we consider case d equal 1 or 2. It is 1 or 2 dimensional case. But physician people can say that 1 and 2 dimensional case not exist. Only we live in 3-dimensional space. And particles move also in only 3-dimensional space. Okay. And we almost be in this potential almost arbitrary. Only I should assume that in momentum representation it should be some continuous function on the torus. Now if we consider coordinate representation, so if the function defined on the lattice, in this case the potential should decay at infinity. Every potential should decay at infinity. But sometimes people consider also other potentials. But, and so our operator is compact operator, integration operator. Result then for any k, the operator H2k has an eigenvalue ek above the upper edge epsilon maximum k of the four-particle continuum. For any b, not 0b, here exists at least one eigenvalue. But can be many, but only this theorem say about existence. And it is only for the, in the case n dimension equal to 1 or 2. And now, if we consider d-dimensional case and d dimension is bigger or equal to 3, in this case it is better to consider some parameter. Parameter defined by this equation. You will see parameter at the S, that in all the lattice depend on S and on K, and S is element of lattice, K is belong to the torus, and here appears some cosine function, and here epsilon maximum is this point, and function epsilon K is dispersion relation. in this case, there is this theorem. If let D bigger or equal 3, and for some S and K, this inequality holds, then the operator H2 has an eigenvalue. Only for some bigger mu or big should be B. Operator has an eigenvalue Ek, and moreover, for any K, this relation is false. This eigenvalue Ek belong here, and for any K, and but Ek less than E0 if K not equal to 0. Okay, and here it's corollary. Corollary says we consider for some S and all K this is inequality holds. If in this case for any K, for all K, the operator H2K has eigenvalue K. It's supposed to explain, because of here I will should a little bit. It is K, and for any K we have this picture, and for any K this is spectrum, and in our case spectrum will be this is, and this kind of, and here appear eigenvalue. It's better to show because of maybe I'll okay, better. No, maybe it's better to show how the spectrum dependence of the spectrum.
Okay, you want the mouse?
You're better, okay? No, I find. Okay. Here, this is what you see that it is two-particle continuum. It is continuous spectrum, and here appear upper above upper edge. This is upper edge of continuous spectrum, and here appear eigenvalue. This eigenvalue for any case appear, it means that there is one bound state at least. And here no bound states, and okay, and here it is here optical loss. It will be to show you here. Okay. Here, two particles interact with the repulsive potentials, and they repel each other. And so here, now it is very important case. It is eigenfunction in momentum space, and eigenfunction, it is very important that eigenfunction has such kind of some form. What it means? to prove existent bound states, you should prove some localization. So it means that if I already, in this theorem, in some cases, we prove that in momentum representation, eigenfunction is analytical function. It means that in coordinate space, it is localized. And if eigenfunction is localized, it means that there is bound states. Okay, it is so momentum representation of the eigenfunction. I should begin. Okay, so yeah, it's theorem, but here some theorem. I don't know. Maybe it is. About two particle operators. I already tell you main results. No, maybe I have not such more time because I would like to say about three particle case. So I have about half an hour. It's better to say half an hour. I have that. It is better to say about three particles because of it was very interesting. It was written. They have experimental results only for the two particle case. But it was written also. It was open problem and no experimental results for three particles. But it is very interesting. In theoretically, for three particles we have results. I would like to tell about this a little bit here. And first of them, because I will tell in lattice case, a view effect in lattice case. So, I will speak now about many body problems. Three particle case already it is called many body, few body, no but many body. There is some motivation. It is very interesting. I found these words in the internet. In 1960, Nobel Prize, winner in physics, Max Born said, it would be indeed by workable in nature 45, except against further advances in knowledge behind the analytical difficulties of the many body problem. It was said in 1960. But you know that Fadeev already in 1964, Fadeev and St. Peter Leningrad mathematician, Soviet mathematician, has solved this problem, not the n-body problem, but n-body scattering problem. But he right also, and many people understand that it is more interesting only three-body case. Three-body scattering problem is more interesting, but n-body problem, people interested, astronomic people interested,